Let's look at some examples of evaluating indefinite integrals. When you're asked to compute an indefinite integral, basically you're looking for an antiderivative, or rather, the general antiderivative. In some cases, this will be very straightforward. Let's look at example A. The indefinite integral of cosine of x dx. This one is fairly straightforward because I know a function that has cosine as a derivative, namely sine. Sine x is an antiderivative of cosine x. The indefinite integral asks for the general antiderivative. So we just add in a plus c, where that c is our constant of integration. Constant of integration. So sometimes you'll know your indefinite integral because you know a derivative. I know that the derivative of sine is cosine, so the indefinite integral of cosine is sine plus a constant. That's fine. And oftentimes you'll find indefinite integrals that you can evaluate in this way. But also often you'll find indefinite integrals that are a little bit more complicated. Example B. Let's say we have the integral of, for example, x squared plus cosine of x dx. This one is slightly more complicated because it's not cosine x or x squared, it's the sum of the two. But that's okay. Even though we don't maybe know off the top of our heads the antiderivative for x squared plus cosine of x, we know the antiderivative for each individual piece. And the integral of the sum is the sum of the integrals. So this is the integral of x squared dx plus the integral of cosine of x dx. And each one of these we can evaluate. The antiderivative for x squared, I say the antiderivative, an antiderivative for x squared is x cubed over 3. An antiderivative for cosine x is sine of x. And then at the end you just tag on a plus c. You don't need 2 plus c's, you only need 1 plus c. Alright, that's example B. Let's do another one. Example C. What happens if you get something a little bit, let's say, less obvious? The integral of x cubed plus x squared plus x all over x squared dx. What about that? This is not something that we necessarily have off the top of our head. This is the integral of a quotient. Now, there is no quotient rule for indefinite integrals. We have a quotient rule for derivatives, but there is no quotient rule for computing indefinite integrals. So you cannot compute the antiderivative of the numerator and the antiderivative of the denominator separately. It doesn't work that way. Instead, what you have to do is you have to ask yourself, is there some way that I can change this integrand and make it look like something that is a little bit more obvious to me? And in this case, we can use some algebraic properties. In particular, we divide. So x cubed divided by x squared is x, plus x squared over x squared is 1, plus x over x squared is 1 over x. Each one of these is a power function, x to a power, and I can integrate all of these. X squared over 2 plus x plus, and be careful you don't forget, this is the natural logarithm of the absolute value of x, plus some constant. So in this problem, we started with something unfamiliar, and we used algebraic properties to change it so it looked a little bit more familiar. Let's try another one. The integral, the indefinite integral, let's say sine x squared plus cosine x quantity squared dx. Here I have the integral of a sum, and at first you might be tempted to write this as the integral of sine x quantity squared dx. plus the integral of cosine x quantity squared dx. And that is a true statement. However, neither of these are any easier to compute than the original integral, so that doesn't really help us much. But it is certainly true that the integral of the sum is the sum of the integrals. All right, well, what else do we do? Well, at this point, we remember the Pythagorean theorem. We refer to our good friend Pythagoras, and we say, Pythagoras, what does this equal? And Pythagoras says, oh, well, sine squared plus cosine squared is equal to 1. Now that's something that we can integrate. The integral of x, oh, not the integral of 1 dx is equal to x plus c. Speaking of trigonometric identities are really your friends when you are computing indefinite integrals. For example, we can use a trigonometric identity to help us actually evaluate the integral of sine x quantity squared or the integral of cosine x squared. Let's look at an example. We can do either one of them. Let's do the integral of cosine x quantity squared dx. What is this? Well, in order to do this, I want to make use of a trigonometric identity, namely that cosine of x quantity squared is equal to 1/2 times 1 plus cosine of 2x. So instead of integrating cosine squared, I'm going to integrate this other expression. So this is the integral of 1/2 1 plus cosine 2x dx. The first thing to do is to take out that 1/2. You're allowed to take out constant multiples. Why can you do that? You can do it because you can do it for derivatives. And now we're looking at antiderivatives. So we're allowed to take out a constant multiple. Now what we want to do is we want to integrate 1 plus cosine of 2x. That's not entirely trivial. This is the integral of, let me put a bracket in there. This is 1/2 times the integral of 1 dx plus the integral of cosine of 2x dx. The integral of 1 dx, that's something that we can do. That's x. But what about the integral of cosine of 2x? What is that? If it was cosine x, we'd be okay. We know that if we, let me write this down, we know that the integral of cosine of x dx is sine of x plus some constant. But what about this cosine 2x thing? What are we supposed to do about that 2x? Well, at this point, let's just think about this in terms of antiderivatives. So if capital F of x is equal to sine of x, I can compute the derivative easily enough. Capital F prime of x, derivative of sine, is cosine of x. So what if I change the antiderivative? So it's not sine of x, it's sine of 2x. What will happen to my derivative? F prime of x is not going to be cosine. I have to use the chain rule. So it's going to be the derivative of sine is cosine of 2x, but then I have to multiply by the derivative of what's inside there, which gives me an extra 2. So what that tells me is that the antiderivative of cosine of 2x times 2 dx is sine of 2x, plus some constant. So really, this is twice what I need. So the integral of cosine of 2x dx is going to be 1/2 sine of 2x plus c. This c here is not exactly the same as the previous c, because I'm dividing it by 2. But these plus c's, these are arbitrary constants, so this plus c can be any constant. So if you take any constant and divide it by 2, it's still just a constant. And you're allowed to choose whichever one you want. So whatever c I want here, I just had to make sure that this c was twice that, and then I divide it by 2. Anyway, this gives us our antiderivative. or our general antiderivative. So we can just take that and plug it right into here, and that gives us our answer. So the integral of cosine of x quantity squared dx is equal to 1/2 times x plus 1/2 sine 2x. And then we put the plus e at the end. Now here we've used various properties. For example, let's write some of these down. The first one that we used that the integral of the sum is the sum of the integrals. This is true because it's true for derivatives. This is a linearity property. We also saw that it was true for definite integrals for different reasons. 2, we also used the fact that constant multiple of f of x dx is equal to k times the integral of f of x dx. So here we have the linearity properties of the indefinite integral. And we saw these for antiderivatives and we saw them for definite integrals. And this is why they both had those properties, because they're related through the indefinite integral. One thing that we do not have, so let me write this as a remark. There is no product rule or quotient rule for integration. For derivatives, you have rules for everything. You have a product rule, you have a quotient rule, you have a chain rule. We don't have these things for integrals. Instead, we have to develop techniques to solve indefinite integrals, where for derivatives you would have a rule. And each rule of a derivative will give you a technique that will enable you to evaluate indefinite integrals. But integration is much more subtle than differentiation. For derivatives, you always have a rule. But for integration, there's not always a rule. So it's more of an art form. You have to construct some way of evaluating integrals. And usually the way you do that is by taking something that you don't know and rewriting it so that it looks like something you do know. We've seen some examples of that here, using trigonometric identities or using simple algebraic properties like what we saw here and here, here and here. Here we used a trigonometric identity, and here we used another one. We could actually evaluate the integral of sine squared in a similar way, using sine x squared equals 1/2 times 1 minus cosine of 2x. That would give you basically the same integral. It would just put a minus sign right there. And so in the end, you'd have a minus sign right here. But otherwise, it's the same. So we could even write that down. The integral of sine x quantity squared dx is equal to 1/2 x minus 1/2 sine 2x plus c. So using techniques like this will enable us to evaluate certain indefinite integrals, but not all of them. Some indefinite integrals cannot be evaluated.